This video will be about radicals. First, I'm going to explain some important properties of radicals. First one says that the nth root of a times b equals the nth root of a times the nth root of b. Another one says the nth root of a over b equals the nth root of a over the nth root of b. Another important thing to note, which is a common mistake, is that the nth root of a plus b does not equal the nth root of a plus the nth root of b. Using the properties we just learned, we can put a root of a number into something called simplest radical form, which means that if we have the nth root of a number x, then we want to convert it into something so that it's a times the nth root of b, where b is not evenly divisible, by any perfect square. So as an example of this, let's say I want to put the square root of 108 into simplest radical form. What I can do is rewrite 108 as, let's just say, 9 times 12. At this point, I can split it using the rules I just learned, the square root of 9 times the square root of 12. And this simplifies to 3 times the square root of 12. But 12 is still divisible by a perfect square, namely 4. So what I'm going to do is rewrite the square root of 12 as the square root of 4 times the square root of 3. Then I can take the square root of 4, and that's 3 times 2 times the square root of 3. So our number in simplest radical form equals 6 times the square root of 3. Now we can add and subtract radicals. So let's say we have something like the square root of 25 n to the fourth times m plus the square root of n squared times m. What we can do is rewrite this as the square root of 25 times the square root of n to the fourth times the square root of m plus the square root of n squared times the square root of m. And this simplifies to 5 times n squared times the square root of m plus the absolute value of n times the square root of m. And then we can factor out the square root of m. So what we're left with is 5n squared plus the absolute value of n, all times the square root of m. Usually when we're dealing with radicals, we don't like to have radicals in the denominator, so we use a method called rationalizing the denominator to get rid of it. This method involves multiplying both the numerator and the denominator by a certain number so that the denominator is now a perfect nth root. For example, if our denominator was the cube root of y, then you would choose the number, the cube root of y squared, to multiply both the numerator and the denominator by, because that way you get as your denominator the cube root of y cubed, or just y. If we had something like a plus the square root of b in our denominator, then we would want to multiply it by a minus the square root of b, because this would give us a difference of squares, or a squared minus the square root of b squared, or just a squared minus b squared. And we see that in both of these cases, there is no longer a radical in the denominator. The second example I've shown here, we do so often that we have a special name for the relationship between these two items. We say that they are something called conjugates of each other, meaning that when you multiply them by each other, you end up getting rid of the radicals.